This mini-lecture returns to solutions and introduces a quantitative way of expressing and calculating concentrations of both compounds and ions in both concentrated and diluted solutions. I previously introduced the terminology for solutions using coffee and tea as an example of an everyday solution. Moving forward, remember that the term solute refers to the substance being dissolved, and the term solvent refers to the substance that the solute is dissolved in. And that water is usually our solvent, since we will be sticking to aqueous solutions in this class. Also recall that the solute can be any type of chemical compound that dissolves in the solvent, and that this breaks solutions into two categories. Solutions of ionic compounds, where ions dissociate in solution, which we also call electrolytes, and solutions of molecular compounds, where the molecules remain intact and do not dissociate, and are also called non-electrolytes. For either type of solution, the concentration of solute dissolved in the solvent can be expressed in terms of the molarity of the solution. And molarity is defined as the moles of solute divided by the total volume of the solution in liters. And written as a mathematical expression, moles are represented by N in chemistry, and volume is represented by V, which is also given in this case in liters. This is a very important note, as liters are the unit that you must use when calculating molarity. So with this, we get an expression of M equals N over V, which we can also rearrange to see that moles of solute in a certain volume of a solution can be calculated simply by multiplying the molarity of the solution by the volume of the solution. In chemistry, the terms molarity and concentration are used pretty much interchangeably, even though there are other units that can be used to express concentration, which we'll see a little later. When preparing a solution with a particular concentration, or molarity, a mass of solute is weighed out and then added to a special flask called a volumetric flask. Then about half of the solvent is added just to dissolve the solute, before finally finishing by topping off with solvent to the line on the volumetric flask. This single measurement line on the flask indicates one set volume with high precision and accuracy, and it cannot be used to measure any other volume than the one it is calibrated for. Therefore, the size of the volumetric flask is selected based on how much solution will be prepared. The molarity of the solution can only be accurately calculated if the total volume of the entire solution is accurately measured, not just the volume of the solvent that is added. By adding the solute to the volumetric flask first, the solvent can then be added until the total final volume of the solution is reached, and this eliminates the need to carefully measure the volume of the solvent separately. Small amounts of ionic solute will usually contribute very little volume to the overall solution as it dissolves and dissociates. So in problems you see in the textbook, homework, quizzes, and exams, it is often okay to assume that the volume of the solution matches the volume of the solvent that the solute is being dissolved in. However, in a practical setting like the lab, this may not always be the case, as some solutes, such as liquids, may contribute towards the total volume of the solution and therefore need to be considered. The definition of molarity of a solution is usually reported per 1 liter of solution by definition, but this value also represents the molarity in any volume of the solution that is created. For example, let's say a lab technician creates 5 liters of a 0.3 molar stock solution for 121 lab. So 0.3 molar concentration means there are 0.3 moles in each liter of the solution. But since the lab tech made 5 liters of solution, then really they would have measured out a total of 1.5 moles to create this 5-liter solution. And that would be the number of moles contained in the solution at the beginning. So even though the molarity is still reported as 0.3 moles per liter, because this is a convention for reporting the concentration, it's important to be mindful about the total volume when considering how many moles are actually present in the solution. So next, let's say that students each take 40 milliliters from the stock solution to use in their experiment. The concentration of each of these 40 milliliter aliquots that each student measures out will be the same as the stock solution, so 0.3 molar. But each 40 milliliter aliquot will now contain just 0.012 moles of the compound or of the solute. And even though the volume inside the stock solution has decreased because of pouring out these 40 milliliter aliquots, the remaining stock solution will also still have the same concentration of 0.3 molar, but the moles of solute left in this remaining solution is now less than the starting 1.5 moles that we began with. So, the concentration or molarity of any volume of a solution will be the same, but the number of moles in the solution will depend on the volume of the solution. This is just like density. Density is the same for water no matter how much water you have, but the mass of a sample of water is highly dependent on the volume of the sample and vice versa. Calculations involving molarity are often confusing for students, so I'll cover a few common types on this slide. First, there is calculating molarity from the grams of solute dissolved in a volume of solvent. This is how chemists determine the molarity of a solution created in the lab. First, since molarity is moles of solute per liter, the grams of solute needs to be converted to moles using the molar mass. Then, the moles are divided by the total volume of the solution, which in this case, we can just assume is the volume of the water that the solute is being dissolved in. I'll also add a conversion factor to correct for units, as the volume I'm dividing by here is given in milliliters instead of liters. So all in all, this leads to 25 grams of sodium chloride being dissolved in 625 milliliters of water to give a resulting solution that has a concentration of 0.6845 molar sodium chloride. Remember that this molarity is also interpreted as 0.6845 moles per 1 liter. Now, alternatively, you could convert the volume of the solution to liters before dividing, and this gives the same answer. So if you're comfortable converting from milliliters to liters in your head, you do not need to write out the conversion of 625 milliliters to 0.625 liters for a problem like this. Now, once the molarity is known, it can be used to calculate the moles or grams of solute in a specific volume, or the volume of solution needed to create a solution from a given mass. To calculate the amount of solute in 12 milliliters of a 0.6845 molar solution, use the molarity as a conversion factor to convert volume to moles, remembering that volume needs to be in liters. Here, I've converted the milliliters to liters in the dimensional analysis first, before using the molarity to finally get the moles. So we can see that 8.214 times 10 to the negative third moles of sodium chloride are contained in 12 milliliters of the 0.6845 molar solution. Or you could also think of this as the amount of sodium chloride that needs to be added to a 12 milliliter volumetric flask when creating 12 milliliters of a 0.6845 molar solution. Now, often I will combine the milliliters to liters conversion with the molarity as shown here, to take care of both conversions in one conversion factor. And this also gives the same answer. Again, many of you may simply wish to start with liters at the beginning of this calculation by first converting 12 milliliters to liters in your head. You can also add one more conversion factor to this calculation by using molar mass to solve for grams instead of moles. Finally, to determine the volume of a solution that is needed to create a certain concentration from a certain mass of solute, I'll again use the molarity as a conversion factor, but this time flipped. This time I started with the mass of solute, converted it into moles, and then used the molarity as a conversion factor, with volume on top and the moles on the bottom. One final conversion factor is then used to convert from liters to milliliters, and we see that 7.75 grams of sodium chloride needs to be dissolved in a 194 milliliter solution to achieve a concentration of 0.6845 molar. Another technique that stock solutions are used for is creating diluted solutions. In this process, a stock solution of very high concentration is used to create a solution of lower concentration by simply adding solvent. Again, a volumetric flask is used for this to ensure that the total volume of the solution is precisely known, and again, this begins by adding solute to the flask, but this time the solute is added by measuring out a portion of a concentrated solution. Then, solvent is added to dilute the solute to the final diluted solution volume. When diluting a portion of stock solution, we are simply adding solvent to a known portion of solute. So that means the number of moles of solute stays the same while the volume of the solution changes, and the change in volume is why the concentration changes. For the concentrated solution, we have a molarity, M1, a volume portion that we've taken from the stock solution, V1, and a number of moles of solute that is contained in that volume portion, N1. For the final diluted solution that we will create, we have a diluted molarity, M2, a final total volume of the diluted solution, V2, and a number of moles of solute that is contained in the total diluted solution, N2. Since the moles of solute in the portion of the concentrated solution is the only source of solute in the diluted solution, then the moles of solute in both solutions are the same, or N1 equals N2. So if we recall that molarity is equal to moles divided by volume, and then rearrange this equation, we see that the moles of solute in the solution can be calculated by multiplying the molarity by the volume in liters. Note how liters cancels out, leaving only moles. So, since the moles of solute in both solutions is equal, we now see that M1 times V1 gives N1, and M2 times V2 gives N2. So if both sides equal each other, then we are left with M1 times V1 equals M2 times V2, or the dilution equation as it is sometimes called. Note that in this equation, the units of volume simply need to match on both sides to cancel out. So you can use milliliters, liters, or any other unit of volume, and this equation will still work out. Now, a word of warning for those of you going on to Chem 122 or for who you use the internet for study resources. There's another form of concentration called molality that is different from molarity, but is often easy to confuse as they have only one letter difference in their names. And the variables are both M, but one is uppercase and the other is lowercase. We will not introduce molality until Chem 122, but keep an eye out for it now so that you don't get confused. There are also many other different ways to express concentration, some of which you may encounter in Chem 121 lab this semester or Chem 122 lab next semester. I've included some on this slide and the next for those of you who would like an easy reference. But we won't be learning about, and I won't be testing on, any of these other concentration units this semester. Finally, recall that our previous introduction to solutions introduced the concept of strong and weak electrolytes as things that produce varying amounts of ions in solution. This concept can now be applied to ionic solutions quantitatively, as we can calculate the actual concentration of ions in solution and compare them to see which solution has a higher ionic concentration and is therefore more conductive. For this, you need to have a good understanding of how ionic compounds dissociate and how to count the number of ions that will be formed in solution. Here we see that magnesium chloride dissociates into one magnesium ion and two chloride ions. So if the concentration of the entire compound is 0.22 molar, then the concentration of the magnesium ions will match, as there is a 1-to-1 ratio between the magnesium ions and the whole compound formula. But for the chloride ions, the concentration will be 0.44 molar, or twice as much, as there is a 2-to-1 ratio between the chloride ions and the whole compound formula. To demonstrate this a bit further, let's look at two different ionic compounds: copper sulfate, which dissociates into one cation and one anion each, and potassium dichromate, which dissociates into two cations and one anion each. Note that the number of moles of each ion in the copper sulfate solution matches the number of moles of the entire compound because there is a 1-to-1 ratio between all chemical species in the dissociation reaction. So if the concentration for the whole compound is 1.36 molar, then the concentration for the copper ion will also be 1.36 molar, as will the concentration for the sulfate ion. If we have the same number of moles of potassium dichromate in the same total volume of solution, then the concentration for the whole compound is the same at 1.36 molar, but the concentration of the potassium ions will be twice as much since there are two potassium ions formed for every one formula unit of the compound, giving a concentration of 2.72 molar for potassium ion, while the dichromate ion will remain the same concentration as the entire compound since it has a 1-to-1 ratio with the compound. So it would appear that there are more total ions in the potassium dichromate solution than in the copper sulfate solution, which we can see by simply adding up the ion concentrations to get the total ion concentration for each solution.